I'm Bryce Adelstein Lelbach. I'm giving this talk. I'm also the program chair for CppCon. So I hope all of you have a great conference. I think we have a really excellent program this year. It's by far the best that we ever had, but I do say that every year. I have been on the C++ Standards Committee for a few years now, and I spend most of my time in this group, Study Group 1, the Concurrency and Parallelism Study Group. And what I want to do with this talk today is I want to arm you with the language and formalisms and mindset of that group. In particular, I want to talk about the C++ execution model, the abstract machine, a little bit about the storage and memory model, and the forward progress system in C++. The reason I wanted to give this talk is that it's taken me a number of years to sort of discover all of these hidden underpinnings of the language. And I think it's really useful information to have. So first, I want to give some caveats about this talk. The first of which is there's this thing in C++ called memory order consume. This talk pretends that it doesn't exist. Because memory order consume complicates a lot of the model that we're going to talk about today. And you're not really missing much if we just pretend it doesn't exist. So we're just going to act as though there is no memory order consume. However, we are going to be talking about the model in C++ 17 and beyond. So it's a little contradictory that we're going to be talking about the latest standard, but we're going to be ignoring this component of it. And there's one other thing that I think you should know before we get really started with the talk, which is the as-if rule. So the as-if rule is a part of the C++ standard that gives implementations the freedom to optimize, to make optimizations that are not observable to the user. So there's certain semantics that are specified in the standard, and your implementation has to abide by those requirements. But if you can make an optimization that you cannot observe that it's sort of cheated, then that's fine. And if you could observe that it cheated in a conforming implementation, you could only observe it through undefined behavior. So this will come up a couple times in the talk. So let's actually get started now. So the C++ execution model. We're going to start by talking about the C++ abstract machine. So what is the abstract machine? The abstract machine is a theoretical model in the standard. It's a portable abstraction of your operating system, your kernel, and your hardware. We as C++ programmers are all familiar with the use of abstractions. And I think that the C++ abstract machine is sort of like the most fundamental abstraction. It's like the first abstraction upon which all other abstractions are built. So you can sort of think of it as the intermediary between your portable C++ program and the system that it is run on. So like you write some portable C++ code, and then you write that portable C++ code to the abstract machine. And then your implementation, whatever it may be, your combination of your hardware, your compiler, your operating system, it provides a conforming implementation of the abstract machine. So we have, on the left, you have your concrete systems that your implementation provides the semantics of the abstract machine to you, and then you write portable code to that abstraction. And this is sort of the root of portability in C++. So the C++ programs describe operations performed on the abstract machine, not on actual hardware. And C++ implementations define the characteristics of the abstract machine and translate those operations on the abstract machine into operations on the system. So this little diagram right here, I sort of illustrate the core parts of the abstract machine, which is really two things. There's threads, and then there's a flat storage space. So C++ at its core is just threads of execution, evaluating functions that operate on objects that are in a flat storage space. That's it. It's a very simple model. So the storage is flat. There's no notion of hierarchy in C++ today. There's no notion of caches or memory hierarchy or NUMA or anything like that. Objects reside in storage at a single memory location. Some objects may not have a unique memory location, such as eligible MT-based classes that can benefit from the MT-based class optimizations, or objects marked with no unique address, which is a new thing that I believe is new as of C++20, not C++17. Now, of course, under as if, an implementation is allowed to store two objects at the same machine address, or not store an object at all. So, like for example, if you wrote a program where you declared some int and you initialized it with a value of 4, and you never take the address of it and you never modify it, then it's not observable in your program whether or not it's stored or not. So the compiler doesn't necessarily need to actually store it in memory. In C++, an object cannot have more than one memory location. This sort of like breaks the model in a couple different ways. And this is the reason why we don't have things like a std mem map. In that if you want to use something like shared memory, you should really do it through volatile. So like, let's consider this code right here. So I have some sort of pointer-like class here, and I have an assignment operator. And in this assignment operator, the first thing I do is I check to see whether I'm doing a self-assignment. Because if I'm doing a self-assignment, I just want to like give up and return star this, because this code will blow up my object. Well, if there were two different addresses that both pointed to this same object, then this check would return false, and I would go ahead here and blow up. So in C++, we have one address for one object. Also, in C++, every thread in a program can potentially access every object and function in a program. So sure, we have things like thread local variables, but if you could take the address of a thread local variable or of a variable on a stack on a particular thread and you pass it to another thread, it can access that object. Any thread can access any object or call any function in a C++ program today. So what are threads? As I mentioned before, I sort of described threads as like being a thing that evaluated a function. So threads of execution are a single flow of control in a program that evaluate a top-level function call and then all of the subsequent expressions within the body of that function. And threads may run concurrently. So like there's the main thread of execution, which all programs have, that evaluates main. And then you can create std threads of execution, which will evaluate some function that you give them. Now, there's also some initialization that happens here. For the main thread, static storage duration objects are initialized before the evaluation of that thread's function and destroyed after that evaluation completes. And for all threads, thread local storage is initialized before the thread function is evaluated, and after it is evaluated, the thread storage duration objects are destroyed for that thread. But I still like to just think of them as threads evaluate a function call. So what does it actually mean to evaluate something in C++? Like what does that actually mean? How does that actually get translated down to actual steps, concrete steps that have to be performed on your concrete system? So to understand evaluation, first we have to understand expressions. And when I say that, I mean we need to understand expressions in the way that the C++ execution model thinks of them. So as it used to be known, the section 1.10 or intro.execution. And not in the sense that you might be familiar of like just expressions in C++ in general as a element of the language. So as far as the execution model is concerned, expressions are a sequence of operators and operands that specify a computation. So like this is an expression that is a function call. It calls function f. The second one here, we've got three expressions. Two of them are sub-expressions, a and b, and then f. This is a expression that implicitly makes a function call to this operator. These declarations contain an expression that calls a constructor here. Sub-expressions are part of a larger expression. So like in this example here, I've got an assignment to a variable here, and I have, so first of all, there's a constructor call here. Then there's this right-hand side here, and the right-hand side here is a function call, and there's two parts of it really. There's the expression that designates the function that's being called here. So in this case, I'm not calling a function by name, but like I'm dereferencing a function pointer. And then I have the expressions for each one of the arguments of the function. And these larger expressions, so the top level expressions are called full expressions. And the way that this is defined is that full expressions are everything that are not sub-expressions. And full expressions appear in statements. So like, for example here, in this if statement right here, this full expression, first of all, there's the obvious, the operator equals equals call. But there's also some conversions that happen here too. And there's also some full expressions that you might not expect, like the destructors are full expressions. And full expressions may include sub-expressions that are not lexically part of the expression. So for example, I have a function here, foo, that has a default argument. And when I call foo with no parameters, this expression here includes this expression right here, even though it's not lexically part of this foo call here. So the evaluation of an expression consists of evaluating two separate parts of the expression. It's value computations and then the initiation of its side effects. So let's talk about the side effects first. Side effects are things that change the execution environment. So reading a volatile object or modifying any object. Calling a library IO function, which is kind of a nebulous term in the spec, but it sort of means what you would think. And calling a function that does any of the above. So side effects are things that that can be observed. Value computations are not side effects. They are things that are pure, that have no observable effect. So the completion of the execution of an evaluation does not imply completion of its side effects. It just implies completion of its value computations. This will be a little bit important later in the talk. So some examples here. In this expression, a equals a plus b, where a and b are ints, a plus b, this is a value computation. But this assignment here is not. This has a side effect because it modifies some object. And the second example here, this is a value computation. But this expression right here, this overloaded shift operator, that calls a library IO function. So it has a side effect. And then this last one here, assuming that we don't know what foo is, well, it may have side effects, it may not. We don't know what foo does, but if foo, the function foo has side effects, then this expression has side effects. So next I want to talk about the two fundamental relations in C++ that describe the order in which things get executed. The first of them is called sequence before. And sequence before is a relation between two different evaluations of an expression within the same thread of execution. So if A is sequenced before B, then the execution of A shall precede the execution of B. And note that little caveat I mentioned earlier that the execution of an evaluation does not, your completion of the execution of an evaluation does not imply completion of its side effects, just of its value computations. The sequence before relation is asymmetric. So A is sequenced before B does not imply that B is sequenced before A. That's sort of straightforward. And it's transitive. If A is sequenced before B and B is sequenced before C, then A is sequenced before C. Each full expression is sequenced before the next full expression in program order, and the side effects of each full expression is sequenced before the side effects of the next full expression in program order. So it's pretty straightforward, like if I have A, B, A is sequenced before B. Now there's two other related relations. The first of them is called indeterminately sequenced. If A and B are indeterminately sequenced, then either A is sequenced before B or B is sequenced before A, but it's unspecified which. But what you do know is that A and B are not interleaved. One comes before the other, you just don't know which. Then there's an even weaker relation called unsequenced. If A and B are unsequenced, then A is not sequenced before B and B is not sequenced before A. and they might potentially be interleaved. So here's a little diagram to help us out here. So if A is sequenced before B, then I know A comes before B. The value computations and side effects of A happen before B. If A and B are indeterminately sequenced, one of these two outcomes happens. It's either A before B, or B before A. And if A and B are unsequenced, then it's either A before B before A, or A and B are overlapped in some way. So let's talk a little bit more about interleaving here. So I'm going to show you a little example that uses some new features. There's one on this slide which is stood for loop, which is a new thing that's in the parallelism TSV2. It's sort of like for each, but it's index-based, not iterator-based. The reason I'm using it here will become a little evident in the next slide, but I wanted something that was very directly mapped to a for loop. In particular, I didn't want to use for each or transform because I wanted to have the assignment be visible in the element function we were executing. If I used transform here, we would just have like return A times X, and that didn't really work for my example here. So I'm also using the parallel overload of for loop, but I'm calling it with the sequenced execution policy, which says, I don't want this to be parallelized. I want you to do this in sequenced order. So like if we were to think about 4 iterations of this loop, and you can think about this operation here, y plus equals a times b, as being consisting of 4 steps. You load y, you load x, assume a is some constant here. Then you do a fuse multiply add of a times x plus b, y, and then you store the result to y. So each one of these colors here is the steps from one iteration. Now, if we change that execution policy from stood execution seek to stood execution unseek, the compiler is allowed to do this. That is, interleave different iterations. So what I've done is I've taken all of the loads of y and put them together, all of the loads of x and put them together, et cetera, et cetera. And one reason you might want to do this is that then you could, instead of doing 4 scalar loads, I could do 1 SIMD or vector load here. Now normally, you wouldn't be able to do this because C++ says, and we'll talk about it a little bit later, you can't interleave people's functions without special permission. But this execution policy gives that special permission. And also anything in C++ that is specified as being unsequenced could potentially be interleaved. So I'm not going to say much about statements, but I'll say that as far as the execution model is concerned, statements are just compositions of full expressions. So like a block statement here, like statement 0 is sequenced before statement 1 here. In an if statement, condition is sequenced before the body. In a while loop, every evaluation of the condition is sequenced before each evaluation of the body. And that transitive property spreads out, as you would imagine. All right, so now let's talk about function evaluation. There's 4 rules I'm going to go through here. They're a little bit wordy, but then we're going to look at an example. So the first rule is when you're calling a function, every evaluation within the body of the function and every evaluation that's not within the body of the function are indeterminately sequenced. This is the property that says you can't interleave my functions. Now, of course, if the compiler can prove that it could interleave your functions under the as-if rule, that you can't observe the side effects, then sure, it could do that. But if it can't, if it would be observable, not through UB, then it's not allowed to because of this rule. The expression designating the function, so the expression designating the thing to call, is sequenced before the argument expressions. And as I said, we'll get to an example, and it'll become a little clearer in a moment. And each argument expression is indeterminately sequenced with respect to all other argument expressions. This is new in C++ 17, slightly changed from before. I believe it was unsequenced before 17. Every expression in the body of the function is sequenced after both the expression designating the function and every argument expression of the function. This is sort of evident, right? The arguments to your function, you need to know what they are before you start executing the function. So we have these 4 rules here. So okay, we're going to look at this example. So I've got some function b. I'm going to call the body of that function b e. And then I have this function g that's not really important. I just wanted to have a full expression to stick g in, and a function called a useful full expression. And then I've got a here, which is just some arbitrary expression that's not part of the body of b. And I've got f, which is some other arbitrary expression, also not part of the body of b. So let's walk through and apply those rules I just showed you. So a and e, this expression right here, and the body of the function are indeterminately sequenced. They can't be observably interleaved. And also, f and e are indeterminately sequenced. That's the first rule I said. This expression right here, and note I put b in parentheses here to indicate it's an expression, not like the actual name of the function. It's some expression that gives me b. That is sequenced before the argument expressions c and d. C and D, as I said, are indeterminately sequenced. Either C is sequenced before D or D is sequenced before C. Both C and D are sequenced before the body of the function. And A through F, everything here is sequenced before the body of that function G. So most of this is pretty straightforward. The only thing that's a little bit surprising is this indeterminate sequencing of function arguments. And this is not true for all operators, and we'll talk about that a little bit later. But let's just look at a little example of where this can be problematic. So let's say I've got some struct here that has some simple constructor, and it has a side effect. If I'm making a function call, so parentheses syntax here, what I get is these two are indeterminately sequenced. The compiler can pick to either do this one and then this one, or to do the other, to do this one and then this one, which GCC chooses to do. Now, if you use unicorn initialization here, it is sequenced, so you'll get from left to right. So this is what GCC gives you, and LLVM gives you the opposite. So this is a little unfortunate, but there were reasons that we didn't fix this. I don't want to get into them too much, but there were reasons. I'm not sure that I agree with the decision we ended up making, but because this is a little painful, but it is what it is. Okay, so now let's talk about operators. So the value computations of all operators are sequenced before the value computations of its operands. This is sort of straightforward again. This set of operators, the operands expressions to these operators are sequenced left to right. And this is true for most of the operators. It's sort of what you would expect. This set, so assignments are sequenced right to left. And this is actually what you expect. It would be surprising to you if you didn't have this, but it's a little unfortunate that it's not consistent across all operators. All right, so now I want to talk about the next relation. So that was just sequenced before. We talked about how, within a single thread, is the evaluation of expressions ordered. Now we're going to talk about how things are ordered between different threads of execution. So within C++, two library operations, A and B, may be related by the synchronizes with relation. So synchronizes with is an asymmetric relation. A synchronizes with B does not imply that B synchronizes with A. So this makes it's a little bit less intuitive than the asymmetric property of sequenced before, because synchronizes with might imply bidirectional, but it's not. So there's a number of ways to achieve synchronizes with the library, with the C++ standard library. So atomic acquire release semantics, mutex lock and unlock, thread create and join, future and promises, and parallel algorithm fork and join are the most common. So let's look at an example to sort of help us understand a little bit better how synchronizes with works. So synchronizes with is a runtime relation. You have to think about who actually observes at runtime the side effects of somebody else. So like in this case here, I've got some simple example where I have a store release and a load acquire. And in this case here, this particular valid execution of this program, this store happened and this load observed the store. And so in this case, there is a synchronizes with relation from here to here. And what that synchronizes with relation means is everything that happened within this thread prior to this is visible to this other thread now. This other thread has observed the side effects of that other thread. But if this thread here did not observe this store here, if this sort of conceptually happened after this load, then you don't have any synchronizes with relation. And note again, synchronizes with is not bidirectional. It's just in one direction. You cannot synchronize from a load to a store, only from a store to a load. Or you can't synchronize with from a load to a store, only from a store to a load. So mutexes, unlock operations on mutexes synchronize with all subsequent lock operations on that mutex. This is a little bit different than the acquire release example where things are sort of paired. And some of the other synchronized with relations are a little more complex than this. So what I mean is, like I've got some lock guard here, and so I have an implicit unlock here, and this unlock will synchronize with all future lock operations. And ditto for this next one here, it'll synchronize with all the future ones. So it sort of fans out to all of the future lock operations that might happen. All right, so we've talked about sequence before. We've talked about synchronize with. Now we're going to talk about happens before, which is, I think, the more common term for people to be familiar with. And what happens before is it's sort of a concatenation of the two. So given any two evaluations, A and B, if A happens before B, then either A is sequenced before B, or A synchronizes with B, or for some evaluation X, A happens before X, and X happens before B. So you can sort of think of it as an arbitrary concatenation of sequenced before and synchronizes with relations. So I think that this is not a great name for this relation, because happens before doesn't mean sort of unquote happened before. Now I'll make a caveat of saying if you're able to witness this, then your program has undefined behavior, right? This should not be observable unless you're using UB. Let's look at a little example here. So I've got some very simple code. I have two variables here, and I have a function foo. There's two assignments in foo. First it does x equals y plus 1, and then another full expression, y equals 1. As we said, full expressions are sequenced after each other. So this is sequenced before, this is sequenced before this. So this should happen before this. But when we look at the assembly here, this actually happens sort of interleaved with this here. So this might seem a little intuitive. It doesn't actually sort of like happen before it in terms of the actual assembly you get out. But you can't observe this. And if you could observe this, the compiler wouldn't do this optimization. Or you'd be observing it through some weird undefined behavior. So happens before doesn't mean happened before. And happening before doesn't mean that you have the happens before relation. So let's look at an example. We got two threads here, and then we have two variables. We have a atomic bool and some data. And I've got a producer thread here, and what it does is it assigns to that data, to that int, and then it does a relaxed store to this ready flag. And then I have this consumer here, and it does if ready, then print out the data. So you would think, perhaps, that if this branch is taken, and if you go here, then you would observe that data is 42. But you won't, because memory order relaxed does not give you a happens before relation. Just because you see this store doesn't mean that you're seeing this store, because you don't have any synchronizes with relation here. So happening before doesn't necessarily mean it happens before. But this is undefined behavior. So the only reason we were able to observe this is because we used undefined behavior. So here's a helpful little chart. Happens before describes arbitrary concatenations of sequenced before and synchronizes with. So sequenced before is the relation that describes the ordering within a thread. And you get that just as a consequence of program order. And synchronizes with is a relation between threads. It's provided by certain library functions. So atomic operations, synchronization operations, parallel algorithms, etc. And I'll make a little reminder, remember, we're not talking about consume here, because this chart and these relations are not as simple and clean when you think about memory order consume. All right, so next we're going to talk about the forward progress system in C++, which is a relatively new feature, or it's been enhanced in C++ 17. So as we said, threads evaluate some top-level function and then all of the expressions contained within the body of that function. And that evaluation of that top-level function, we can separate it into execution steps. So threads take execution steps towards completion of that function. Or you can think of the execution steps delineate different stages of the evaluation. So an execution step is one of these things. It's either the termination of the thread, so like the thread's done, makes sense, an access of a volatile object, either a read or a write, or the completion of a library I/O function call, or a library synchronization operation, like mutex lock or unlock, or an atomic operation. So all of these are execution steps, and you can sort of think of these as like the stages of the epochs of the evaluation of a function. So one note here, some atomic operations may fail spuriously due to interference from other threads. And implementations are encouraged but not required to prevent these spurious failures from indefinitely preventing a thread from making forward progress by executing execution steps. In practice, the fact that this is encouragement and not a guarantee is not really a problem. The place where this comes up is on a load-locked store conditional architecture, where another thread might repeatedly steal the cache line you're operating on in between the load-locked and the store conditional instruction, just because like it needed some other data on that cache line. And like in theory, like that could just like delay you forever. But in practice, it's not really a concern. There's other forward progress concerns in C++ that are a bigger deal, but it's worth mentioning at least. So, I think we stepped over a slide there. We stepped over a slide that said threads make progress by executing execution steps, or it'll magically appear later. So I want to briefly take a little aside to describe how we model blocking in the standard library. It's sort of relevant to forward progress. So blocking, the definition in the standard is to wait for a condition to be satisfied before continuing execution. Or we'll often say in standardese, like to block pending this event happening. Like to block pending the completion of this thread. To block pending this mutex becoming unlocked. Something like that. Blocking library functions are modeled as continuously executing execution steps while waiting for their condition to be satisfied. And thus, blocking makes progress. This doesn't mean that they're necessarily implemented in this way. That they don't have to be actively spinning, but they have to make progress if your implementation wants to implement them another way. So forward progress guarantee is that something observable should eventually happen in your program. Like that your program eventually will terminate. This is like a really bad paraphrasing of something Chandler said at the bar last night at like 2 a.m. So I should have like a Chandler Carruth quote up here, but I didn't want to embarrass him on the slide just with my words. So implementations are allowed to assume that all threads will eventually perform an execution step. This has an important caveat, which is that infinite loops that have no observable side effects are undefined behavior. And this is important. It's important for this to be undefined behavior because it's important for the compiler to be able to optimize loops even when it can't prove that the loop terminates. Like, for example, loops where maybe you're like going through a circular buffer or something like that, or where it's difficult for the compiler to infer whether the loop terminates or not. So this guarantee that implementations can assume that you haven't put, while true into your program, although I don't want to dive into that one in particular, is important for compiler optimizations of loops. So there's 3 types of forward progress guarantees that threads can give you in the standard. And they are concurrent forward progress, parallel forward progress, and weakly parallel forward progress. So concurrent forward progress is the guarantee that the thread will make progress regardless of whether other threads are making progress concurrently with it. So even if there's other threads like doing stuff, your thread will make progress. It will execute execution steps, and eventually something will happen that's observable. So some examples of things that give concurrent forward progress: preemptive OS thread scheduling, something like a fair share OS thread scheduling or round robin OS thread scheduling, or an unbounded thread pool. An unbounded thread pool will be a thread pool that you create it with some number of threads, but then if it needs to add more threads to ensure forward progress, it would do so. So this is a very strong guarantee, and it's very desirable because it makes it easy for you to ensure that your program has forward progress and that your program will, your stuff will eventually run. Parallel forward progress is a little bit weaker. What it says is once a thread has executed its first execution step, it will make progress. So once it's executed its first execution step, then it has concurrent forward progress guarantees until it terminates. So once it's started, you know that it'll have forward progress. So some examples: run to completion user space tasking, or hybrid threads, or user space scheduling. There's like a billion names for this. I hope I used one of them that you're familiar with. Or something like a bounded thread pool, where you've got a thread pool, you've got a fixed number of threads, and it will execute functions, run those functions to completion, but it won't add new threads if needed to make forward progress. And threads on modern NVIDIA GPUs, so Volta and later, will give you parallel forward progress guarantees. So then we have weakly parallel forward progress guarantees, which is really just you don't get any progress guarantee at all. So the thread's not guaranteed to make forward progress. So there's a lot of things that fit this model. So non-preemptive OS thread scheduling, suspendable user space tasking, so something like work stealing task schedulers, things where your threads will voluntarily, your user space tasks will voluntarily preempt themselves, or fibers. Threadless asynchrony, something like coroutines, lazy execution can sort of be thought of as a thread of execution that has weakly parallel forward progress guarantees. One that I forgot on this slide here is SIMD lanes can be thought of as modeling weakly parallel forward progress. And threads on non-NVIDIA GPUs and older GPUs, or legacy, as we've said here. So what guarantees does the main thread in C++ make? Like the thread that runs your program. What do you think you get? I want to hear some answers. What do we think we get?
Weak parallel.
Okay, weak parallel. Anybody else? Okay, I hear parallel. Concurrent. So it's actually implementation defined. There's a note that says general purpose implementations are encouraged to give you concurrent forward progress guarantees. But like if you're implementing like a hard real-time system, you just can't do this. Or if you're implementing a system where you don't have a scheduler at all, where like you just have one core and it's an embedded system and you just run on the bare hardware, like you don't have any way to make this guarantee. Like each thread will just run until completion. So it's implementation defined. What about stood thread threads? Anybody? The same here? Yeah, it's the same. It's also implementation defined, of course. So again, most implementations will give you concurrent forward progress guarantees, but on some platforms, like embedded platforms, real-time platforms, you might not get this. So there is a mechanism in the standard which is got a mouthy name. It's a block with forward progress delegation, but there's a nickname that we give it within study group 1, which is boost blocking. And what boost blocking does is it is a mechanism for blocking on a thread with weaker forward progress guarantees while preserving the calling thread's forward progress. So this is very useful when you're dealing with non-concurrent threads of execution. So the sort of semantics of what it does is when you have a thread P that boost blocks on some set of other threads, the forward progress guarantees of at least one of the threads in S is temporarily upgraded to the forward progress guarantees of P, and then this continues until S terminates, and then you repeat this until the blocking condition is satisfied, and you go and get other threads from that set that you're blocking on if you need to. It is unspecified which threads or which order of threads are picked from that set. So boost blocking is a way to ensure that your children threads, work that you spawn, makes progress, but it's not necessarily a way to make sure that your siblings make progress. The reason I point this out is that boost blocking is not a magical solution that prevents you from deadlocking a lightweight work stealing task scheduler that only gives you weekly parallel forward progress guarantees. It gives you some protection. In particular, as I said, it will ensure that your children threads make progress, but not your siblings. So here's like an example of what I'm going to call a lazy thread. This is like a very simple, really bad sort of stood thread-ish implementation. So it's just a thread, like it's really just like a stood function that is in a class. It's very boring. Stood function void. And I've got, this is like what join would look like for this. So if I've still got the function here, when I call join, then I need to ensure that it will run. And one way to do that is for me to just run it. And this would be boost blocking, because whatever my current forward progress guarantees and my current calling thread of execution are, this thread, the conceptual thread that executes this function, will run with those forward progress guarantees. And then otherwise I just throw, because that's what join does if you call it twice. And I like assign it out to be something that will return false here. So a slightly more advanced example, let's imagine we have some sort of thread pool where we've got a single queue of tasks. This is the queue here. And then I have some number of worker threads, and what the worker threads do is they check whether this is empty or whether they've been signaled that like the thread pool is being shut down. And if it's not empty and if they're not done, then they go and get something out of the queue, and they go and execute it. And so these tasks in the queue, we can think of these as threads of execution. And so let's look at a little code example here. Let's say that I've made some static thread pool here. And then I'm going to go and like give it some work to do. I'm going to say, go execute this task on this thread pool here. And this is sort of creating a thread of execution on this thread pool. And let's say that inside of this task, what I do is I say, I'm going to, I want to parallelize whatever the work is that I'm doing. So I'm going to create 2 children tasks on this thread pool, this same thread pool here too. And then like I'll go do some other stuff, and then like I'll join on them. But what if I just had one thread in this thread pool here? So what would happen is like I would put this task in the queue, it would start executing this task, then it would add these tasks to the queue, and then it would join and block on those tasks, and then it would just keep blocking forever because there's no other thread in this thread pool to run this task. So what needs to happen is in these join methods here, we need to do boost blocking. We need to upgrade the forward progress guarantees of these children here. We need to sort of give them use of our thread until our blocking condition is satisfied. And that is boost blocking. All right, so here's sort of the takeaways that I wanted you all to get from this talk, sort of 4 main points here. The C++ execution model in a sentence is threads evaluating expressions in a flat storage space that contains objects that are accessed and manipulated by those threads. Evaluations within a thread are the order of evaluation within a thread is driven by the sequence before relation. Interactions between threads are driven by the synchronizes with relations. And forward progress sort of gives us a system by which to ensure we have eventual termination of our program. All right, I've got about 5 minutes left, which is a good amount of time for questions. So I don't know if, I can't really see if there's microphones here. Doesn't look like there are. Maybe there are in the back. Do we have microphones? Okay. Anybody have questions? Maybe stand up or make yourself visible-ish to me. I see Michael back there.
Right. Can you go back to the boost blocking definition slide?
The question was, can I go back to the boost blocking definition slide? This one?
Yes. Now go back one more slide.
Yep.
Oh, maybe not. Go forward.
This one?
Yes. Does that ensure what you have written there? So what you said is that it's only for children of the thread and not siblings. But does that?
It only guarantees that your children will proceed. Like, as an example, let's say I've got like a, so the question was sort of, what do you mean about it only ensuring progress for your children and not your siblings? What I mean is, like, let's say I've got a thread pool with 2 threads in it, and I enqueue 3 tasks, each of which, or I enqueue 3 tasks, each of which wait on a 4th task that I enqueue. So now in my queue, I have 3 tasks that wait on a 4th task that's in the queue, and I've got 2 threads in my thread pool executing it. So each one of those threads grabs one of the first 2 tasks that blocks, and they spin waiting for that last task. And then, like, I have some other thread, some other concurrent execution agent that then goes and boost blocks on this queue, and like it grabs the other task that blocks. And it just also doesn't make any progress because I have 3 threads now that are waiting for this 4th task, and there's nobody to execute it. You can only boost block to delegate, to give use of your thread to your children. You can't prevent unrelated tasks that are siblings that are of the same execution cost or within the same execution context. Well, you can't ensure that they will progress because you don't really know what they're doing, and you don't even necessarily know how to find them. Does that help at all?
Yes.
Okay. The point I'm trying to make is that boost blocking does not magically guarantee that weaker than concurrent threads of execution will not deadlock when you use synchronization primitives designed for concurrent execution agents that will block the underlying concurrent execution agents that are implementing your weaker execution agents. I see a question.
I have the microphone.
Oh, okay, there's a microphone. We'll go with whoever has the microphone.
Why did we assume in the start of the talk that STD memory order consume does not exist?
Why did we assume that STD memory order does not exist? Hang on. Well, the reason is that this chart is pretty straightforward and fits on a slide. And when you have to deal with memory order consume, there's another relation, strongly happens before, that fits in here, and it gets more complicated, but explaining this to you without memory order consume gives you the basic idea. The basic idea being sequence before gives you your evaluation order within a single thread, and it's a consequence of program order, and synchronizes with gives you relations between threads. So memory, like the complexities of the wording of the standard to make memory order consume work don't change the underlying model. They just like complicate it in ways that I don't think are interesting to discuss here. Like if we had like, you know, a full day workshop. Sorry, what was the second comment? Yes, yeah. All right, I see there's a queue.
Yeah. So if you go early on, if you're going early on, there was a side effects and an observable. There was an expression A equals A plus B, but why in that assignment is that actually a side effect in your slides?
Because you're modifying some object.
But you said it was only if it was volatile or I/O, or just modifying a value causes a side effect?
Hang on, we'll get there. The question was, is modifying a non-volatile object a side effect?
You passed it. There, keep going. Keep going.
Reading a volatile object or modifying any object is a side effect. Yeah,
Thank you.
Yeah. Yep. Ansel?
In your answer about the boost blocking, you implied but didn't say that you can only boost block a call that sort of hasn't started executing yet. Is that an accurate way to look at it, or is there more complexity there?
The question is that I seem to imply that you can only boost block a call that has not started executing yet. Not necessarily. Here's an example. Let's say that I've got some sort of work-stealing thread scheduler like HPX or something like a coroutine or a fiber, where I've got some sort of task that is suspendable. One thing I could do while boost blocking is resume and continue the execution of one of those suspendable tasks. Next up.
Can you please elaborate a little bit about why using atomic Boolean causes undefined behavior?
Because, so the example was, hang on. Let's see if we can find that one. The question was about the use of, a little bit further, was it back here? You know, I think we should maybe follow up on that later because I know which slide you're talking about. I don't remember where it is in the deck. But the answer was that example I was using memory order relaxed, the store and the load, and that doesn't give me a synchronizes with relation. So I had something where I had like some assignment to some data and then like do a relaxed store to some guard variable, and then in some if statement do a relaxed load of that guard variable, and then assume that if I saw the guard variable be marked as it's ready, then I knew the data was ready. You only get that with acquire release semantics. You don't get that with relaxed. Relaxed doesn't give you any memory ordering guarantees about what, like, doesn't mean that because I've observed this atomic load, I don't know anything else about observing other things that happened in that thread before the store.
Yeah, I think it would be worth to follow up afterwards because I think atomics could be used to synchronize access to other data.
All I would have had to do to make that not undefined behavior is change it from a store relaxed to a store release, and from a load relaxed to a load acquire. That's all, and then that example would have been fine.
I see. And on one small kind of confusion, I think you mentioned execution model unsec, but
yes.
It should be execution model parallel unsec.
I put stood : execution : unseek, which I believe is the namespace that we ended up putting them in, but we changed it a couple times.
I see. Thanks.
All right, I think last question.
Okay, could you go back to the slide where you introduced an execution step?
Hang on, I kind of remember where that one was.
Yeah.
Yeah.
Can you elaborate on what does library IO function call mean? How do you define an IO function?
The question was, can I elaborate on what the library IO function is? I wish I could. A library IO function is not a well-defined term in the standard. I don't think we have a definition for it. I'm not sure if we label things in the library section as saying like this is a library IO function. My guess would be that I know that we don't have a definition of it. We might just use it as a term of art in the library section, but I think from the last time I looked, it's just a thing that we talk about in the execution model that we don't really explain what it is. And it's sort of like, it's just common knowledge. So I would have to consult with more senior SG1 wizards than I to give you a good definition of that.
But can I assume, for example, like any system call that causes a context switch is an library IO function call, or it depends?
No, no, I don't. I'm not comfortable saying anything other than like cout and printf are library IO functions.
Okay, thank you.
Yeah.